So, hello everyone. My name is SUKRIT, and today I will be talking about Gram-Schmidt orthogonalization. What is Gram-Schmidt orthogonalization? Gram-Schmidt orthogonalization is a process by which a set of vectors V, say V1, V2, V3, so on and so forth till Vk, are converted to a system of k orthogonal vectors, namely V dash is equal to V1 dash, V2 dash, V3 dash, so on and so forth till Vk dash. One extension of Gram-Schmidt orthogonalization is termed as Gram-Schmidt orthonormalization, which, as its name suggests, applies a similar process. However, instead of the final result being a simple orthogonal set of vectors, it is rather a set of orthonormal vectors. Gram-Schmidt orthogonalization finds its application in various techniques of linear algebra, such as, but not limited to, eigenvector determination, particularly in the context of spectral and SVD decompositions. Further, it also finds itself being useful in the case of QR and RQ decompositions, two special decompositions which are also usable when solving an inverse problem as the spectral and SVD decompositions. In physical applications, we find that in quantum mechanics, one of the most preferable methods to orthogonalize a system is Gram-Schmidt orthogonalization. This is despite the fact that there do exist multiple other techniques which are much more sophisticated. However, the preference towards the Gram-Schmidt process arises due to its simplicity and elegance in terms of both intuition and process. Now, what exactly is the intuition behind the Gram-Schmidt process? Effectively, as you can see here, what we do is we take two vectors, say V1 and V2. We choose our first vector as the base orthogonal vector. We term that as U1. Then we calculate the projection of V2 along U1. And since that part will not be counted in the next orthogonal vector, we remove that component of V2 and we are left with U2 simply. And when we normalize these two vectors, we can get E2 and E1, which respectively represent the orthonormal set of vectors, right? This GIF shows how it works. So essentially, we first took V1 and V2, and since we chose V1 is equal to U1, we remove the component of V2 which lies along U1, and we are left with U2. Then we extend this to the third vector by removing its component along U1, which can be seen as follows. We are left with we are left with V3 dash. From here, we remove the component of V3 dash, which also lies along U2, and we are left with U3, which is the third orthogonal component. We can now further normalize these three vectors to get the orthonormal set of vectors. See here, we can see U1, U2, and U3 form an orthogonal set, whereas when we normalize them, we get E1, E2, and E3, which are both normal and normal at the same, orthogonal and normal at the same time. Now, why Gram-Schmidt? Compared to other orthogonalization schemes, Gram-Schmidt offers certain advantages. For instance, one of the basic advantages in terms of complexity is that it can produce the jth orthogonal vector at the jth iteration of the process. However, other processes like householder transformations will produce all the possible orthogonal vectors at the end of the simulation. Further, it is a very intuitive and simple to understand algorithm, as shown here, where we simply just remove the components which lie along previously discovered orthonormal vectors or orthogonal vectors to discover the next orthogonal component. Further, it also has an interesting property known as, which does not affect its properties in linear algebra. However, it is of much interest in geometry and other applications. This is basically the concept of orientation. This means orientation refers to a specific notion of how the vectors are arranged in this, how the vectors are given precedence in the vector space. And one of the properties is that the orientation of the original set V1, V2, V3 is the same as the orientation of the next set, which is V1 dash, V2 dash, so on and so forth. One possible application of this is in the exterior product, where orientation is used to determine how the exterior product is going to take place. However, unlike any other method, it also presents its own set of limitations as well. one of the most basic limitations of the Gram-Schmidt process is its numerical stability. Numerical stability refers to those types of refers to issues in computation which arise due to rounding errors, for instance, in computers. Um, however, we can formulate a more numerically stable version of the Gram-Schmidt process as compared to the original process, known as a stabilized Gram-Schmidt. Further, it also fails, i.e., Gram-Schmidt process fails to produce an orthogonal set of vectors when the set of vectors are not linearly independent. However, this limitation is not necessarily the fault of Gram-Schmidt orthogonalization, since it holds for other orthogonalization schemes. And one of the major assumptions before applying an orthogonalization scheme is to check whether or not the set of vectors is linearly independent or not. Now, first, let us look at the basic algorithm for orthogonalization. We take an input of vectors, namely v is equal to v1, v2, v3, so on and so forth. And our goal is to output a set of orthogonal vectors v dash, where v dash includes v1 dash, v2 dash, v3 dash, so on and so forth. At the first step, i.e. at I is equal to 1, we take v1 dash is equal to v1, i.e. our first orthogonal vector is chosen as the first vector of the set v. To compute the next ith orthogonal vector in v dash for I is greater than 1, we assume that the first I minus 1 have already been found. From here, we select the ith vector from v, namely vi, and we orthogonalize it to the first I minus 1 orthogonalized vectors as follows. We use vi minus the projection of vi along each of the orthogonal vectors, right? One of the advantage, what this does is basically this, but for any general number of vectors. Here we took v1 is equal to u1, and then we subtracted the projection of v2 along v1 to get the second orthogonal vector. To account for the, as mentioned previously, two of the limitations of the Gram-Schmidt process are in terms of its numerical stability and in the case when all vectors are not linearly independent. Instead of one possible way to prevent this from happening is during the iteration process, we can check if after each iteration, if any of the orthogonal vectors obtained is actually a zero vector. When this happens at the ith iteration, we know that we can say that the set of vectors is not linearly independent, and thus we cannot create an orthogonal set of k vectors for v. However, in this case, the first I minus 1 vectors which were obtained do form an orthogonal basis. Further, we can improve this modification as well to get all possible orthogonal to form the orthogonal basis for the entire set by checking for each subsequent iteration by removing all the zero vectors which we obtain, and the final set of vectors which we obtain after applying the Gram-Schmidt process successively, disregarding the zero vectors, that represents the orthogonal basis for the given set of vectors. Further, to improve the numerical stability, basically the floating point errors associated with computation, we propose we can use a modification which reduces the numerical error produced in each step, and this works on an iterative procedure. And further, we can also convert the orthogonalization process into the orthonormalization process by simply dividing each obtained orthogonal vector by its L2 norm. The L2 norm is obtained by the dot product of a vector by itself, as the square root of the dot product of a vector by itself. So the numerically stable algorithm goes as follows. The first step is still the same as the original one, namely at I is equal to 1, we choose the first vector in our set as the first orthogonal vector. Next, to compute the further orthogonal vectors, assuming the first I minus 1 have already been found, we select the ith vector from V, orthogonalize it to the first I minus 1 orthogonalized vector successively as follows. So in each iteration, we take Vi as the Vi of at the jth iteration is Vi at the j minus 1th iteration minus the projection of Vi at the j minus 1th iteration along the Vjth orthogonal vector. What this does is successively it reduces the error by ensuring that the computationally each vector is orthogonal to the first choice of vectors. We also include the modification we introduced previously. If Vi dash is equal to 0, we end the process, and else we continue the process for the further set of orthogonal vectors. Now, Previously, I mentioned that Gram-Schmidt orthogonalization finds its application in a specific type of decomposition known as the QR decomposition. What exactly is the QR decomposition? Like any other matrix decomposition, QR decomposition represents the factorization of a matrix, say A, into as the product of two matrices, Q and R, where Q is an orthogonal matrix and R is an upper triangular matrix. One important thing to note is that unlike decompositions like SVD, which apply to all cases, the special case of QR decomposition is restricted to those matrices where M is greater than equal to n, where the dimensions of A are m cross n. Basically, this means that the number of rows should be much more than the number of columns in A, right? Further related to the QR decomposition, we also obtain the RQ, QL, and LQ decomposition, and each of these further have their own reduced versions. I will first introduce the QR decomposition and extend their algorithm for the QL, LQ, and RQ decompositions. The algorithm to calculate the QR decomposition can involves orthogonalization, which can be done using the Gram-Schmidt process. Further, QR decompositions and LQ decompositions particularly can be applied to solving most systems of linear equations of the form AX is equal to B. Since, as mentioned previously, they do make an implicit assumption regarding the nature of A, i.e. it is i.e. M is greater than equal to N, and that the system is further consistent, i.e. none of the equations form an inconsistent set of systems, and this holds for most physical applications unless a systematic error during calculation has been made. So the mathematical overview for the QR decomposition is follows. We take the matrix A and we choose its column vectors, namely V1, V2, so on and so forth till Vn, right? We calculate its rank as the dimension of the column space, say K. We know that using the Gram-Schmidt orthonormalization on the set of V1 to Vn, we will get a set of K orthonormal vectors from the column vectors, namely V dash is equal to V1 to V1 dash to Vk dash. Excuse the lack of V2 dash over there. Then we also know that we can reverse construct each of these. We can reverse construct each of these vectors from the orthonormal vectors using Vi is equal to using the formula shown below. Mathematically, we can express this in the form of a matrix as follows. Here, V1 dash, V2 dash, and Vk dash are the orthogonalized vectors, and the next upper triangular matrix shown next to it represents the reconstruction of V1, V2, so on and so forth till Vn on multiplying each of the following vectors. Now, you may notice that does not produce a set of square matrices, since Q dash has a dimension of n cross k, whereas R dash has a dimension of k cross n. This factorization is specifically known as the reduced QR decomposition of A, where R dash can also be expressed as Q dash transpose A, using the property of orthogonal vectors. However, we can convert this into standard QR decomposition by extending Q dash with m minus k vectors so as to complete the orthonormal basis for Rm, and adding the corresponding 0 rows in R dash, since it will still remain as an upper triangular matrix. From here, one obtains the QR decomposition of A as QR, where Q is an n cross m square matrix and R is an upper triangular m cross n matrix. Further, similar to R dash, we can also express R as Q transpose A. Now, as mentioned previously, we can also relate the QR decomposition to the RQ, LQ, and QL decompositions. The QR decomposition of A is equivalent to the LQ decomposition of A transpose, as shown below. If I write A is equal to QR and I take its transpose, I get A transpose equal to R transpose Q transpose. Here R transpose is a lower triangular matrix, which we can call L, and the obtained orthogonal matrix Q is simply the transpose of the original of the orthogonal matrix obtained for A. Thus, we can apply. Thus, we can use this concept to apply the LQ decomposition of any matrix A by calculating the QR decomposition of its transpose, since the definition extends both ways. Right. Further, the RQ decomposition is related to the QR decomposition, that while in the QR decomposition, as seen here, we apply this orthonormalization on the set V1, V2, V3 in that specific order. However, in the case of RQ decomposition, we apply the Gram-Schmidt process starting from the last row vectors, where in QR we use the column vectors of A, in RQ we use the row vectors of A. Basically, the lowest row of A is considered as V1, then we have V2, then we have V3, so on and so forth, until the topmost row is considered as Vn. As shown above, the since I mentioned above, the QR decomposition of A is equivalent to the LQ decomposition of A transpose and vice versa. Similarly, we can say that the QL decomposition of A is equivalent to the RQ decomposition of its transpose, and again vice versa. Now, this also has an application in solving a system of linear equations, whether it is an overdetermined or underdetermined system. Particularly, this can also apply in the determined case. However, we are taking that as a trivial extension, since both these cases cover both the determined and overdetermined. And the next case, where we apply the same process for an underdetermined system, also preserves this process, applies for the determined system. For an overdetermined system, we notice that the number of equations, m, basically is much more than the number of variables. Thus, we can use the QR decomposition of A. Assuming we have the QR decomposition of A, we can write it as QRX is equal to B, or using its reduced QR decomposition, that Q dash R dash X is equal to B. We can pre-multiply by Q, and Q dash inverse is equal to Q dash transpose, but in the case of the non-reduced QR decomposition, and that will yield R dash X is equal to Q dash B. Now, since R dash X is an upper triangular system, we can simply apply back substitution as we did in the case of Gauss-Jordan elimination on Q dash B, and this will give us the solution for the overdetermined system. Practically, the benefit is that this is the minimal residual norm solution to the system, i.e. this is the solution for which the norm of the residuals, namely Ax minus B, is minimized for the given X, for any X. Further, in our other course named by the name of Optimization in Soft Computing Techniques, we also discussed the concept of solving an overdetermined system for the overdetermined case and obtaining the minimal residual norm solution using the pseudo-inverse. For a consistent system of equations, we can obtain the pseudo-inverse simply as X is equal to A transpose A inverse A transpose B. This will yield us the minimal residual norm solution, which can be proved through calculus, the details of which I will not get into due to the time constraints and the practical, and due to the absence of linear algebra in that theory. Further, we previously obtained that the QR decomposition of A is equal to Q dash R dash, and substituting this in the minimal residual norm solution as obtained for the using the normal form of the equation, we can see that each of these steps ultimately reduces it into the same result that we got for in the previous explanation. Basically, we re-get that R dash X is equal to Q dash B is equivalent to using the minimal residual norm solution as solved using a convex optimization technique. Further, for an underdetermined system, the solutions of A and further for an underdetermined system, however, we cannot apply QR decomposition, since as mentioned previously, QR decomposition only applies when the number of equations m is more than or equal to the number of variables n. Thus, in this case, we can use the QR decomposition of A transpose, since the QR decomposition of A transpose applies when m is less than equal to n, since A transpose in it is an n cross m matrix. As we know, the QR decomposition of A transpose is equivalent to the LQ decomposition of A as shown in this slide, or as mentioned in this slide. Further, we can from A transpose is equal to QR, we get A is equal to R transpose Q transpose. Substituting this, we get R transpose Q transpose X is equal to B. And if we consider the reduced QR decomposition, we get R dash transpose Q dash transpose X is equal to B. Now, if we take Q dash transpose X is equal to X dash as some transformation applying on the original vector X, we get R dash transpose X dash is equal to B. Now, since R dash transpose is lower triangular, we can also apply back substitution. However, this time of using going from the top to the bottom as compared to the back substitution for an upper triangular system where we start from the bottom and go to the top. Right. So once we apply simple back substitution, we get R dash transpose inverse B as our solution to X dash. And further, since X dash is obtained by multiplying an orthogonal matrix into X, we can pre-multiply it again to get the original vector X. And even in this case, we can see that this R dash transpose so obtained is the minimal residual norm solution to the system Ax minus B. Here, as you can see, I mentioned that this is an implicit assumption. However, that R dash transpose is an n cross m matrix, i.e. all the rows in A are linearly independent. And this is a necessary condition to solve it in the case of an underdetermined system. Unlike SVD, which can apply to any generalized system of equations through the pseudo-inverse, the QR decomposition and RQ decompositions apply only in certain cases subject to certain conditions, such as the one mentioned over here. Generally, this, as mentioned here, these decompositions provide the solution when the system is not only consistent, but also satisfies either the column when it's overdetermined that it is consistent, and when it is underdetermined that it forms a set of linearly independent row vectors. Similarly, as compared to the as we justified the case of the overdetermined system, we can also justify the underdetermined case using again the result from convex optimization, where we get the result as X is equal to A transpose inverse B for the underdetermined system. Excuse the use of the word underdetermined, overdetermined over here. And on back substituting A transpose as back substituting using the reduced QR decomposition of A transpose, which is equivalent to the LQ decomposition of A, we get the same result as we derived in the previous slide. Now, I mentioned previously in the first slide that the Gram-Schmidt process has specific application in the case of spectral decomposition and SVD. This is because whenever we perform spectral decomposition and SVD, we must calculate the eigen decomposition for a symmetric matrix. In the case of spectral decomposition, since A itself is supposed to be symmetric or Hermitian for the case of a complex matrix, we must directly calculate its eigenvalues and eigenvectors. Whereas in the case of SVD, given a matrix A, we must calculate AA transpose and A transpose A to get its SVD version. Using the spectral theorem, which is a theorem which states that any Hermitian matrix or symmetric matrix in the case of real numbers can be converted into a system of orthonormal eigenvectors, basically justifying that for any Hermitian matrix, its eigen decomposition of the form Q transpose lambda Q must always exist. We use this result to know that whenever we have a root of geometric multiplicity more than one, basically say our eigenvalues are lambda 1, lambda 2, lambda 3, so on and so forth till lambda n. If we notice that for some lambdas, say lambda 1 is equal to lambda 2 is equal to lambda 3, we must know that there also exists 3 corresponding linearly independent eigenvectors. Further, by the result of spectral decomposition, these 3 linearly independent eigenvectors must be convertible into an orthogonal system of vectors, and that can be done using the Gram-Schmidt process to orthogonalize these vectors. Similarly, we can apply this for the case of SVD as well, which is equivalent to finding the spectral decompositions of AA transpose and A transpose A to find U and V and sigma as well. Now, this is just a theoretical tidbit. The previous algorithm we saw for applying the Gram-Schmidt process is a very iterative algorithm, and each of these steps have to be calculated separately. However, we can also create a system which solves it, solves the Gram-Schmidt orthogonalization problem using the process of Gaussian elimination. The justification for this will not be discussed since it is beyond the scope of the discussion. However, basically, we consider the augmented matrix AA transpose, where we consider A to include all the row vectors where we consider A to be the set of all row vectors of a matrix, and where we need to orthogonalize the row vectors of say A, or given a set of vectors V, we can convert it into a system A where its row vectors are V1, V2, V3, and so forth, so on and so forth. On applying Gaussian elimination to the augmented matrix AA transpose concatenated with A, using only the elementary row operations of adding a scalar multiple to one row to another, we so as to obtain an upper triangular matrix in the place of AA transpose. The vectors of the resultant matrix in the place of A represent the orthogonalized vectors. Simply, we see that applying Gaussian elimination using only the elementary row operation of adding a scalar multiple, we get A transpose concatenated with A becomes U, where U is an upper where U is an upper triangular system concatenated with A dash, where A dash represents the orthogonalized set of vectors. One of the most, here we did not use any other elementary row operation apart from adding a scalar multiple of one row to another. Namely, we did not use the operation of switching rows. This is because, as mentioned previously, Gram-Schmidt orthogonalization preserves the orientation of the vectors used during the normalization procedure or orthogonalization procedure. Further, we did not divide it by any, we did not use the elementary row operation of dividing by a scalar, dividing a row by a scalar. This is because because we do not wish to because we do not care about orthonormalizing the system. Since after we obtain the orthogonalized set, we can simply divide each of these by their L2 norms to get the orthonormalized version. Now, furthermore, this is not the only way we can solve Gram-Schmidt orthogonalization. We can also do it in the form of determinants. Now, this result was shown using Gram determinants, which are a specific class of determinants for a set of vectors as defined here. For a set of vectors Vi is equal to V1 through Vi, we can obtain the Gram determinant. Excuse me. We can obtain the Gram determinant as di is equal to v1 as the dot products of each vector with itself and with the other vectors across each row. Further, we can use this result for any vector vi for any vector to obtain its orthonormalized version. Here it must be noted that when we talk about v1, v2, and vi in the last column of the above equation, they act as total vectors. We do not calculate their norm, L2 norm, or anything. We directly use them as vectors with all their independent components. Similarly, we can obtain the orthonormalized version as well if we use the second expression instead. Now, this concludes the theoretical discussions on Gram-Schmidt orthogonalization. I will also discuss I will also show one application of orthogonalization for a set of three linearly independent vectors, and I will also demonstrate a coded version of Gram-Schmidt orthogonalization, which will yield similar results. Thank you. So, hello. As mentioned previously, once the presentation was over, now we will discuss Gram-Schmidt orthogonalization with an example. This example is a fairly standard example, which only changes with the choice of vectors. So here it is as follows. Okay. So let us consider that we are given a set of vectors v1 is equal to 3, -2, 4. v2 is equal to 0, 1, -2, and v3 is equal to 2, 3, -1. This is a set of vectors v is equal to v1, v2, v3, which we need to orthogonalize to a system v dash is equal to v1 dash, v2 dash, v3 dash, which is orthogonal, and a system v double dash, which is v1 double dash, v2 double dash, v3 double dash, where this system is orthonormal. Now, as mentioned in the algorithm, since we first need to calculate v1 dash, we take v1 dash is equal to v1. That is simple, and we can obtain V1 double dash as V1 upon norm of V1. V1 is equal to 3 minus 2, 4. And the norm of V1 is equal to root of 9 plus 4 plus 16 is equal to root of 29. So V1 V double dash is equal to 1 upon root 29, 3 minus 2, 4. Now from here, now we need to obtain V2 double dash. V2 double dash is not orthogonal directly to V1 dash. So what we do is we take V2 and we subtract the projection of V2 along V1 dash. Now, how do we calculate the projection? As mentioned in the previous, PPT, we can calculate this by taking the dot product of V2 and V1 dash, dividing it by the dot product of V1 dash with itself, and the projection is along V1 dash. So we pre-multiply it or post-multiply it since this is a scalar. We can pre-multiply it with V1 dash. So effectively V2 dash is equal to 0, 1, minus 2, minus, calculating the dot products, we have 0, 1, minus 2, and 3 minus 2, 4, divided by 3 minus 2, 4, and 3 minus 2, 4. And this is all along 3 minus 2, 4. Here we use the property that the dot product is calculated between two vectors V1 and V2 as V1 transpose V2 is equal to V2 transpose V1. Now, further from here we get V2 dash is equal to 0, 1, minus 2, minus. On the top we get minus 10, and on the bottom we get 29, whereas 3, minus 2, and 4. Subtracting these components, we get 0 plus 10 by 29 into 3, that is effectively 30 by 29. And in the second component, we get 1 plus 1 minus 20 by 29, which is equivalent to 9 by 29. And we get minus 2 plus 40 by 29, which is equivalent to minus 18 by 29. We can normalize this by here we can also extract 3 common. So we get 3 by 29 into 10, 3 minus 6. So from here we get V2 double dash is equal to, we can remove this scalar multiple since it will effectively get cancelled out when we do V2 dash upon norm of V2 dash. We can simply use this one to get 10, 3 minus 6 upon root of 100 plus 9 plus 36, i.e. root of 145. This is our V2 double dash. Now, to calculate V3 dash, we have to use, we take V3, we remove the projection of V3 along V1 dash, i.e. we remove that component of V3 which lies along V1 dash, and we also subtract the projection of V3 along V2 dash. And as mentioned previously, we can calculate the projection vectors. So we effectively get V3, 2, 3 minus 1 minus, the projection is calculated as 2, 3 minus 1, 3 minus 2, 4, upon 3 minus 2, 4, and 3 minus 2, 4, along V1 dash. And also we can only take this component, or we can take the entire V2 dash since the scalar part will always cancel out. But let us take this entire the entire V2 dash as it is. So we get 3 by 29 into 2, 3 minus 1 along 10, 3 minus 6, and then 3 square by 29 square, 10, 3 minus 6, 10, 3 minus 6, all along 3 by 29 of 10, 3 minus 6. Now, we see that 3 by 29 cancels from both the numerator and the denominator, and we are left with 2, 3 minus 1 This leaves us with upon 29 we have minus 6 minus 6 minus 4. So we are left with minus 4 by 29 into 3 minus 2 4. And we are also on applying this, we have upon 145 10 3 minus 6, we have 29 minus 6, which is 29 2 3 minus 1. Okay, this is minus 1. So 29 plus 6, which is 35 upon 145. Taking 5 common, we are left with 7 upon 29. And we can find that this is equivalent to 2 plus 12 by 29 minus 70 by 29, which is equivalent to 2 minus 58 by 29, which is equal to 2 minus 2 is equal to 0. Then we have 3 minus 8 by 29 minus 21 by 29, which is equivalent to 3 minus 29 by 29, which is equal to 3 minus 1 or 2. And we have minus 1 plus 16 by 29 plus 42 by 29, which is equivalent to minus 1 plus 58 by 29, or minus 1 plus 2, basically 0, 2 and 1. From here we can also obtain the orthogonal version of V3 dash as V3 dash upon norm of V3 dash is equal to 0 to 1 upon root of 0 plus 4 plus 1 is equal to root 5. So from here we had initially the set 2, 3, minus 1. Oh, sorry, the order matter. The set was 3, minus 2, 4, 0, 1, minus 2, 2, 3, minus 1. And from here we obtain V dash is equal to 3 minus 2, 4 directly. 3 by 29 into 10, 3 minus 6, and also 0, 2, and 1. Now we can verify that this set is certainly orthogonal by saying that if we multiply that V1 dash, V2 dash is equal to 30 minus 6 minus 24 is equal to 0, and V2 dash, V3 dash is equal to 10 is equal to 0 plus 6 minus 6, again 0, and even V1 dash, V3 dash is equal to 0 minus 4 plus 4 is equal to 0. From further, we also obtained the orthonormal set of vectors as by dividing each of these by their respective norms as 3 minus 2, 4 upon root 29, 10, 3 minus 6 upon root 145, and 0 to 1 upon root 5. We can verify that these are orthogonal since they are obtained by just dividing this by a scalar multiple. So the if the dot product is 0, it is preserved as 0 itself, and by dividing it by their norm, so they are they also have a norm of 1. Okay. Then we will. This was the numerical law, Gram-Schmidt orthogonalization and orthonormalization. It is to be noted that here we could apply the numerically stable version of V3 of the Gram-Schmidt orthogonalization by, instead of calculating V3 dash as V3 minus projection of V3 along V1 dash minus projection of V3 along V2 dash, this represents the numerically unstable method, since the error magnifies at both additions. However, we could have instead calculated V3 dash as V3 dash is equal to, at the first iteration, we only calculate V3 minus projection of V3 along V1 dash. This would yield us 3 minus 2, 3 minus 1 minus, since this is the same term as before, we can see that this was Simply minus 4 by 29 into 3 minus 2, 4. Minus 4 by 29 into 3 minus 2, 4. From here we get V3 dash at the first iteration is 2 plus 58 plus 12. 58 plus 12 is equal to 70 by 29. This is 3 plus 3 minus 8 is equal to 29 into 3 is 70 again. And this one is minus 1 plus 4. 29, 16 minus 29 is equal to minus 13. Wait. 58 minus 58 plus 12, 70. 3 minus 2, 4. 3 plus 3 minus 8. 70, and then minus 1 plus 16, minus 29 plus 16 is equal to minus 29 plus 16 is equal to minus 13 whole upon 29. Then we could have calculated V3 dash at the second iteration, which is equal to the V3 dash we actually need as V3 dash at the first iteration minus the projection of V3 dash at the first iteration along V2 dash. This is calculated as 70 minus 13 into 1 by 29 minus 1 by 29 into what 3 by 29 of 77 of 70 wait 70 minus 13 70 10 3 minus 6 into upon 3 by 29 whole square 10 3 minus 6 10 3 minus 6 into 3 by 29 of 10 3 minus 6. Cancelling 3 by 29 we get 70 minus 13 into 1 by 29 minus 1 by 29 into this becomes 145 700 plus 210 910 plus 18 928 988 yes 700 plus 210 910 plus 60 970 plus 18 988 upon 145 since 988 divided by into 10 3 minus 6. Okay, so from here we obtain 70 into 140. Okay, so there was actually a mistake at this step. 70, it should be 70, 79 and minus 13 minus 29 plus 13. So yes. So from here we have to change this 70, 79. Right. So we get 700 plus 79 into 3, that is 937 plus 13 into 6, which is 78, and we get 1015. Now it is to be noted that 1015 is a multiple of 29. So we get 35, and from here subtracting, we get 7 and 29. So from here we get 1 by 29, 70, 79 minus 13 minus 7 by 29 into 10, 3 minus 6. This is equal to 70 minus 70, 0. 79 minus 21, which is 58 upon 29 equal to 2. And minus 13 minus 13 plus 42, which is 42 minus 13, which is equivalent to 29. So 29 by 29, which is equal to 1. As can be seen, we get the same result. However, when it comes to computers calculating it, they perform much better with the stable version as compared to the unstable version. Now, this was applying Gram-Schmidt orthogonalization. Now we will see a code example to calculate the QR decomposition of a 3 cross 3 matrix. That 3 cross 3 matrix is A is equal to, let me check once, A is equal to 12 minus 51, 4, 6, 167, minus 68, minus 4, 24, and minus 41. Here, since we know that when we calculate A is equal to QR, we should get a set of 3 normal vectors, E1, E2, and E3, which are where A is equal to V1, V2, and V3. Right, so where this is A, and we get A's, this is our Q, and our R is E1 into V1. Wait, let me make this in a separate place. R is E1 into V1, E1 into V, E2 into V1, wait, let me check. E1 into V1, then we have E1 into V2, then E1 into V2, E1 into V3, 0, 0, 0, E2 into V2, E3 into V3, and here we have E2 into V3. This corresponds to the formula for the QR decomposition as I showed in the presentation, which I will share once again when I'm presenting the code. So if we take a certain case where A is equal to 12 minus 51, 4, 6, 167 minus 68, minus 4, 24, minus 41. Now here we notice that when we apply the QR decomposition of A, the Q matrix which we obtain, it will be equivalent to the, its column vectors will represent the orthonormal set of V dash is equal to V1 double dash, V2 double dash, V3 double dash, where V1 double dash is equal to 12, 6 minus 4 minus V2 is equal to V2 is equal to minus 51, 167, and 24, and V3 is equal to 4 minus 68 minus 44. Here we get the corresponding orthogonal for this system. And first let us run the code and show the same diagram as we showed previously for the QR decomposition, and then we can verify the result obtained from there. So let me share my screen. Okay. So as can be seen here, the formula I mentioned for the QR decomposition. It's not loading properly. Yes. So the QR decomposition, as shown here, we have the column vectors. We will orthogonalize them into a system of into an orthonormal system, and we will calculate the components as follows. Effectively, we wish to not only verify that our result is the same as the result obtained here, but we also want to show how QR decompose how we can use Gram-Schmidt orthogonalization for the same. Let us take let us open. Wait, let me open my Zoom. It is showing some technical glitches. Um, okay, so this is my code. I did not write this code by myself. However, I only made some minor modifications to a code which was presented as an open source code on GitHub. So let me rerun this program. Since we have a 3x3 matrix, then we can successively enter each of the elements. I've already prepared that, and see, we get the same matrix. Sorry. Here we notice that first we have to here, since as noted in the code, we have to enter the successively the column vectors of A, and as noted previously, the column vectors are 12, 6, -4, -51, 167, 24, and 4, -68, and -41. This is equivalent in entry wise, it represents the transpose. However, as you will see later, it calculates the same matrix. So this is when my code is asked to display the original matrix, and as you can see, it is the same as the one is shown in the notes. And here we obtained the column vectors which represent the orthogonalized vector sets. Let us keep notice these values. And we also obtain the matrix R as follows. Further in this code, there is a section which can numerically verify that the set obtained is an orthonormal set, and it can be seen that with minor lack of precision over here, where the error is of order magnitude of 10 to the power of -17 and 10 to the power of -16, we see that this is a very accurate code for calculating for calculating the orthogonalization of this given set of vectors and for calculating the QR decomposition. Now let us go back to the notes and verify that this result is equivalent to the previously to the QR decomposition of A. Sorry. So here we obtained Q is equal to 0.857 0.857 minus 0.394 minus 0.3314. Yeah. So we obtained Q is equal to 0.857, 0.428, 0.286 minus 0.394, 0.903, 0.171 minus 0.331, 0.034 minus 0.943. And we obtained R as 1421 minus 14, 0, 175 minus 70, 0, 0, 35. Now, when we calculate A is equal to QR, the result we get, apart from some rounding errors, is approximately similar to the original matrix, which is 12, 6, -4, minus 57, minus 51, 167, 24, 4 minus 68 minus 41. Here we can see it is to be noted that when we calculate 7Q, we get a very simple result of, we do not get this, we do not get ugly fractions or decimals. Instead, we get a very simple result that 7q is equivalent to, 175q is equivalent to 6 into, sorry, 6 by 7. So we get 150, 75 minus 50 minus 69, 158, 30 minus 58, 6, and minus 165. This is a very clean matrix, and and this is obtained by our code itself. Basically, effectively, I tweaked the code so that instead of outputting Q itself, it will output 175Q. And in that case, I obtained the following matrix. And this, when I verify that 175QR, I get it is equivalent to 175 A itself. So that is a very consistent result. I will share the code for this in the description below. And from here we see that we can use Gram-Schmidt GS orthogonalization for both calculating the orthogonal set of vectors as shown in an example above, orthogonal set. We can use it to calculate an orthonormal set, and we can use a stabilized algorithm of the same. Further, we also discussed it for in the case of QR decomposition, which, as discussed in the presentation in much detail, can be used to solve a system of linear equations. Further, we also saw in the presentation itself that Gram-Schmidt orthogonalization can be used for SVD and spectral decomposition when we need to calculate the orthonormal eigenbasis for a symmetric matrix of A when A is equal to A transpose, or this is for spectral decomposition, or of AA transpose and A transpose A in the case of SVD. So this shows that how much Gram-Schmidt orthogonalization can be useful, and we also saw that it has many practical applications such as quantum mechanics, where it is used to obtain an orthogonal system of vectors. That is it for Gram-Schmidt orthogonalization. The next section of the PPT will discuss a completely unrelated topic to Gram-Schmidt orthogonalization, known as quadratic forms.